Hello, welcome back to Calculus. Here we're talking about exponential growth and decay. I have three problems here. They are kind of hybrids in the sense that they're problems, but they're also kind of lectures. So you're expected to not know everything here. We're going to do some problems, but we're also going to be learning along the way. All right, exponential functions are around us everywhere. If there's one thing that I could impart to you before leaving this lesson, is that in everyday life, if you're ever given some kind of either a loan or a credit card contract or a debt or something like that where something is happening at a certain percentage every single month, you see that's trying to trick your brain. Anytime something's happening at a fixed percent every single month, we can show that it always equates to an exponential function. And remember, exponential functions start very, very flat, but once they gain steam, they go very, very vertical, very, very fast. It's a great way to go into debt and not be able to pay it back because you don't see the effect of it in the beginning, but then after things compound for a long period of time, suddenly you owe a lot of money to somebody. So all of the credit card contracts, the bank loans, anything like that is always at a certain percent per month, right? And the first problem, we're going to show how things compounding, a certain percentage at a certain frequency, how that equates to being an exponential function. So here we go. If an insect population increases by a constant percentage every month, why is the number of insects represented by an exponential function? It's a very open-ended question. There's no equation in here. There's no numbers in here. So we have to kind of make up something as we go, right? So we're going to use equations that are abstract, but let's first talk about the population, right, of these insects. And let's pretend that the population grows 10% or 20, let's say 20% per month. 20% per month. And let's say that you start out with 1,000 insects. What would that look like? Well, it has to be some function of time. So it has to be 1,000 and then some other stuff after it. Well, what does it mean to increase by, let's say, 20% every month? Right? So what it would be 1.20 to the power of t, right? And how do I know that this is the correct equation? Well, when you have t is equal to 0 months, and then you have t is equal to 1 month, and then t is equal to 2 months, and then 3 months, and then 4 months, and so on. If you put a 0 in here, then you're going to get 1,000. That's your initial population. If you go 1 month into the future, then you take the 1,000 that you have, and then you multiply by 1.20, which is, as you know, is a 20% increase. So yes, 20% is 0.2. That's the percentage. But since we're saying it's increasing by 20%, you need to multiply by 1.2 to make it get bigger by 20%. All right, there we go. Now, to move over here, it's going to be at 2 months in the future, it'll be 1,000 times 1.20 to the power of 2. This is one here was the power of 1. So if you start with this and multiply by 1.2, you get this. If you start this and multiply by 1.2 again, then that's why it's squared. So you can already see that the concept of increasing by a certain percentage, multiplying by a certain percentage every month, it leads to an exponent here, there. That is, and that's sort of that is the initial concept of the exponential gain that's really going on there. So you could sort of stop right there, but let's just keep going and try to learn as much as we can from it. So here is a concrete example. We increased by 1.2%. Something you might see in a calculus textbook would be a little bit more formalized. It might say that instead of I, let me use P, the population at 1 month in the future is going to be the population at 0, the initial population, right, multiplied by 1 plus some percentage k over 100. You see, this already looks so much more complicated, but it's the same thing that I'm telling you here. You start with some initial population, and you're multiplying by something. You're multiplying by 1 plus whatever the percentage is divided by 100, converting it to a decimal. Then you add 1. That's how you get something like 1.2, and then you're multiplying by the initial situation here. And if you don't like the p of 0 here, then a lot of times what you'll see in books is you'll call it p naught multiplied. So this is like the initial population times some percentage, okay? And then what would it be? What would the population be at 2 months? Well, it would be what you started with here at 1 month, and then you'd multiply again. So it would be p sub 0, 1 plus k over 100. And you have to take this, which is the previous month, and you're going to multiply it again by 1 plus k over 100. This is exactly what I just showed you right here, okay? So what you would say is that the population at 2 months is p naught times 1 plus k over 100 to the power of t. Or I should say, since it's 2 months in the future, we'll just replace this with a 2 here, because when you multiply these together, that means it's that quantity squared. And so if you wanted to know what the population was at any point in the future, it would just be the initial population, 1 plus k over 100 to the power of t. Now, doesn't this look so much more complicated? I could have started the lesson with this and said, hey, this is, you know, what it looks like when you multiply by a percentage every month, and you would say, what does that mean? So I go through this whole thing, and you could see that it's the same thing as just multiplying by 1.2 or 1.5 or whatever it is over and over again. But still, even though there's an exponent here, if I say that something is an exponential function, we usually want to see a base e in there somewhere. How can we make this, or is this thing equivalent to a real exponential with a base e? Well, never forget that any exponent that you have, any exponential function you have, you can write it in terms of base e, right? And so we'll just do that real quick. What you can say is that you could say, what you can do is you could say, well, I have some initial population. I can write it as e to the power of natural log 1 plus k over 100 to the power of t. So all I've done is I've said e to the power of natural log of what I have here. How can I do that? Well, because the natural log and the e exponential function are inverses. So they annihilate each other. So these cancel, giving me back what I have started with, which means that writing this like this is perfectly legal to do. All right, now since I have a logarithm here, if I want to, I can bring this t over here, and I can say p naught e to the t natural log 1 plus k over 100, like this. Now, even though you may or may not love the way this thing looks, this is an exponential function, p of t. So if I give you this and I say, is this an exponential function? 99 out of 100 people would say yes. Why? Well, because you have an e to the power of some stuff. Now, everything inside of here is ultimately going to be a constant dictated by what my percentage increases every month, the k. That's like increasing by 20% per month. Or 20 is k, 20 divided by 100 is 0.2, and then 1.2 when you add it there. So this is just going to be a number, and then you have that time in the exponent there. So when we see e to the power of t with anything, we know it's an exponential function. But when you look back at the original problem statement and I just say, hey, insect population, it increases by a certain percentage every month, is it exponential or not? Most people will say they don't know, or they'll say no. Okay, but anytime something is happening, multiplying by a constant multiplicative factor every month like that, you'll always be able to recast it as an exponential function. If you graph this thing, it has an e to the t in there. It is going to go just like an exponential function that you may visualize before. So this is what I would circle if I wanted to show somebody that this constant multiplicative, like a population growth thing, or it could be debt, or it could be a loan repayment or something like that. Anything with compound interest, where interest is applied at a certain frequency, it's always calculated based on your previous month's balance. So it's increasing more and more and more every month, and that yields an exponential growth. Now we're going to see the same thing in the next problem, but it's going to be taken one step further, and I do not expect you to be able to solve this ahead of time, but we're going to learn some stuff along the way. It says a bacteria culture starts out with 100 cells, and it grows at a rate proportional to its size. After an hour, the population has increased to 420. How many bacteria are there after T hours? And also, what is the rate of growth after T hours? So rate of growth, we know we're going to take a derivative somewhere in there. All right, but how do we proceed? We have to read every bit of this very carefully. A bacteria culture starts with 100 cells, and it grows at a rate proportional to its size. Grows at a rate proportional to its size. So we're going to use X to represent the population size. So what we basically have figured out is that the derivative of the population, that's X right there, with respect to time, it grows at a rate proportional to its size. That means it's proportional to its current size. So the bigger the population is, then the higher the rate of growth. And that's how a bacteria usually happens anyway. Now, to write it down a little more mathematically, instead of this proportionality thing, what we can do is we can say dx dt is equal to k times x, right? So instead of just saying it's proportional, we just introduce a constant of proportionality. All we're saying is that the rate of change of population growth with respect to time is proportional with a proportionality constant, k, which is a constant, times the size of the population. Now this is called the differential equation. We're going to solve, you'll have an entire class in differential equations down the road where you learn how to solve these kinds of things, right? For right now, this is why I say I don't expect you to be able to solve it, but we're going to learn a lot from it. I'm going to tell you that the solution to this thing is some constant c times e to the k times t. That this is the solution. When we try to find the differential equation solution, what we're trying to figure out is what is x of t? What is the population as a function of time? We know that the rate of change of the population is equal to this. What is the population equation itself? And I'm telling you this is a solution without any proof. However, we can get comfortable and we can show that it's true by plugging it in over here. We can take the derivative of this. Basically, we plug it in here and take the derivative and then we plug it in over here. So what is the derivative of this? If we have c e to the kt, is this equal to kx? Right? And if we take the derivative of the left-hand side, like what we're supposed to do over here, is that equal to what is on the right-hand side over there? So if we take this derivative, this is a constant, so it's going to be constant, then e to the k times t, because that's an exponential function, but then it has to be multiplied by the derivative of the numerator, which is just a k, like this. So what we have here, when we bring the k here, we have well, actually, if you notice, c e to the kt, that is defined to be, let me write over here, kx. c e to the kt, that is what we said x was. So we can put an x right here. X times k is equal to k times x. So the left-hand side is equal to the right-hand side. So again, it's a little bit of a circular argument. I haven't showed you how to solve these. I'm just telling you that this is a solution to this. And I know it's a solution because when I put it in here and take the derivative, what I get on the left-hand side, once I take that derivative and I realize that this is what x is, that it's equal to what I have said the right-hand side is. And so it satisfies the differential equation. Just like in algebra, you put it into there and you calculate that the left and the right-hand side is equal. All right? Now, we have to go a little bit deeper with this one. We now know that this is the solution. However, we have a constant sitting out in the front, and we're told the bacteria starts out with 100 cells and it grows at a rate proportional to its size. After 1 hour, the population's increased to 420. But backing up for a second, yes, it increases after 1 hour, but what happens at 0 hours? In other words, it implicitly tells us that time 0, it starts out with a population size of 100. So that means if this is the population, then that we're going to have a population of 100 at time 0. If we put time 0 into this equation, then we should get a population of 100 out. But anything to the 0 power is 1. So what we have is c times 1. And so that means that this constant, which I didn't know what it was in the beginning, is now locked down because in the problem it tells us how many bacteria we have at time 0. That's called an initial condition. By knowing at time 0 what the answer is, we can figure out what this constant is. And so that tells me that I can take this equation, which I know has to be the answer, and I can refine it. Since I know now this constant is 100, e to the kt. This is a better refinement of this equation. It's not totally locked down because there's another constant up here, but it's at least more locked down than it was before. Okay? Now, next, we're also told that after 1 hour, the population increases to 420. So again, I can start with this, and I can say that 420 is the population at 1 hour in the future. So I put 1 hour in here, and I put 420 here, and I'm using the most fully up-to-date version of the equation that I have here. And so I'm going to have on the left-hand side 420 over 100 when I divide by this, and it's going to be e to the k on the right-hand side, like this. The goal is I want to figure out what these constants are running around the equation. So how do I figure out what k is? Well, first of all, let's just simplify this. So e to the k, 420 divided by 100, it works out to be 21 over 5. If you strike the zeros, you'll get 42 over 10. And then when you simplify further there, then you're going to get 21 on the top and you're going to get 5 on the bottom. So this is the answer here. Now, how do I solve for k? I need to take the natural log of both sides. So e to the k right here, natural log here, 21 over 5, like this. All right, and so what I'm going to get is that this k value is the natural log of 21 over 5. Now, natural log is just a function, so if I put a number in here, it's still going to give me a number out. All right, so what I can say here is that the most revised, up-to-date answer that I have for my population, which was this one right here, is now x is equal to 100 times e to the power of k, which I've now figured out, natural log of 21 over 5, natural log of 21 over 5 times t. So this natural log is right here. I can move the t in front, so x is going to be 100, e to the t, natural log 21 over 5. And when I have something multiplied by a natural log, I can put it into the exponent. That's just a law of natural logs. So I'm going to get 100, e natural log 21 over 5, and then that can go right there, like this. And now I can eliminate, because I have an e and a natural log which annihilate each other, and so it's going to be 100 multiplied by 21 over 5 to the power of t. This is the best version of the equation that we have. This is the population as a function of time. So what I'll do is say x of t, like this, and I'm just going to circle it. I'm just going to circle it here, and it encapsulates, I think, cleanly what this problem is really about. It's telling us that we start with a population of 100 at time 0. If you put 0 in here, then you're going to get 100, right? And then every hour as we go on, we're multiplying by the ratio 21 over 5. And so we're increasing it every unit of time into the future that we have right here. So this is exponential. You have a base here and you have an exponential of t, an exponent of t, and so it is an exponential growth kind of situation. Now the problem says we start out with 100, we grow at a rate proportional to our size. After an hour, the population gets to 420. How many bacteria are there after t hours? That's what we just figured out the answer to right here. What is the rate of growth after 3 hours? So let's go over here. And we're going to write this equation down again. X of t is 100. Then we're going to have 21 over 5 to the power of t. This is the population size. Now we want to know now what the rate of growth is. So x prime of t. How do we take the derivative of this thing? Well, this is a base. It's a weird fractional base, but it's just a number to the power of t. We know how to take derivatives of that. First of all, the exponential remains indestructible, 21 over 5 to the t, right? But then we have to multiply by the natural log of the base, so 21 over 5. This is something that we've learned in the past, how to take derivatives of general exponential functions. The exponential function itself remains intact, and then we have the natural log of the base there as another constant right there. All right, so this is the rate of change. So if we have x prime, and we're trying to find out what it is at 3 hours in the future, let me double check. What is the rate of growth after 3 hours? If we put 3 hours in here, we're going to get 100. Then we're going to get 21 over 5 to the power of 3. Then we have natural log 21 over 5. So let me double check myself. 100, 21 over 5 to the power of 3, natural log of 21 over 5. And this works out to 10632.25. And that's bacteria per hour. Because over here, this was just bacteria, because this is the population size. I can't even spell right, bacteria, right? Here, and when we take the derivative with respect to time, we're getting a bacteria, I can't spell bacteria here either, bacteria, per hour. So this is the growth rate at this moment in time. That's how many bacteria is increasing per hour at this time. But as time goes on, the rate's increasing, because you can see that the actual derivative has a function of time in there as well. So as time goes on, not only is the bacteria size increasing, but the actual rate is increasing as well. So you, just like with bacteria, when your money grows or when your debt grows. It's very, very, very small at first, but it can get to be very, very, very big, very, very, very fast, because not only is the population size or the amount of money you have or the debt you have getting bigger, but the rate of accruing more debt is getting bigger also, or accruing more money if you're investing. So that's why we say it's very important to start investing at an early age. And it's very important not to take on too much debt, because if you take on debt at an early age, it grows exponentially as well. So approximately 10,632.25, that's what it works out to be. And here is the population as a function of time and the rate of change, the derivative of the population as a function of time. So I can't really say that this problem was one that you should know how to do ahead of time, because there was some differential equation stuff in there, but it's very, very good to learn about. I mean, you only learn by doing, right? So we said we had the population growth rate was proportional to the size of the population. And that means that it's equal to some constant times x. And then I gave you without proof, and I told you that this is the form of the solution. You learn how to find this when you take a differential equations class. You can verify it's true by plugging it in, taking the derivative on the left and on the right, and you see that it checks out. This is the form of the solution. At 0 hours, the population started out to be this much. That allowed us to find the constant c, so we revised the equation. Then at 1 hour in the future, we knew what the population was, and that allowed us to find k, which is just this weird natural log of a number, but it's just a number. So that's k. So here's the revised equation, right? And then once we get it like this, then we get rid of the exponential. We kind of like put the exponent back in place, and then we get rid of the e and the ln. They cancel out, and then here is our final answer there. Of course, you could just say this is the answer too, but this is a little bit simpler, so we go with this. This is the population as a function of time. Now the growth rate, we take the derivative, which we know how to do with arbitrary exponentials, and then we get the bacteria growth rate as a function of time. All right, just a couple of little problems there to understand bacteria growth or exponential growth and decay. Now what we need to do is do a whole arrangement of different kinds of problems in the next several lessons to get you comfortable with taking derivatives and solving word problems. Those are called related rates problems. These have been word problems as well, but in the next few lessons we have some more rigorous problems called related rates. We have several of them because we have to get very good at them, and so that's what we're going to work on in the next lesson. Learn anything at mathandscience.com.